Okay, so let's keep going with our group theory review. I really got to say, I'm loving this idea of digging into the group explorer and playing with and exploring, literally exploring the groups. And then as issues come up, we talk about them, and that is our review of group theory. I didn't do it this way when I was a student, right? We did it by axiomatic principles and going through proofs and the hard work that I think is necessary for a first course. But for a review, I think it's way more fun to go through this group explorer, which didn't exist, by the way, when I was a student. So I'm having a lot of fun with this. So we've already studied group D4 in detail, right? So we've done this group here. Oh, that's a little thick. So we studied D4, and we got, and I talked a lot about the subgroup lattice for D4. So one thing I missed is I didn't talk, I think, enough about the cyclic subgroups. So I think now is a good time to remind ourselves how cyclic groups, not just cyclic subgroups, but cyclic groups work. Sometimes you end up saying subgroups a lot when you mean groups, but they're all the same. Subgroups are just subsets of other groups, right? That's pretty easy. But the cyclic groups on the Group Explorer are all given by these z sub integer, right? So, and there's one cyclic subgroup for each integer, right? And z9, z10, z11. So obviously, if we understand cyclic subgroups, we understand a heck of a lot of these smaller groups. So it is worthy of review. Now, the basic principle is, let's look. Obviously, these groups are related, right? They're given the same name. They're given a certain type of name, and there seems to be an infinite number of them. There are. So we turn to the group presentation to see what's the similarity. And it's very, very straightforward. If there is only one generator, you are dealing with a cyclic subgroup. Let's look. We see Z1, one generator, cyclic. One generator, cyclic. One generator, cyclic. One generator, cyclic. And when I say cyclic, I mean it's one of these Z's, right? One generator, cyclic. And basically, if you have only one generator, then there's only one possible string of elements of the group. It's the generator. Let's see, the generator A. Then there's A squared. Then there's a cubed, and then there's a to the fourth, and then there's a to the fifth, and a to the sixth. Of course, I'm looking at Z9 right now. And a to the seventh, and a to the eighth, and a to the ninth. Oops, but a to the ninth by the relation equals 1, so that one's gone, and you add the identity element. You wrap them up in a set, and there's your group as a set. And the multiplication table is pretty obvious also. You could derive that very quickly. So all cyclic groups have that structure. Here it is, 11, 12. Is there a group with one generator that's not cyclic? Well, you got to imagine, what other relation would you have? If all you can do is A, well, I could say maybe A squared equals A cubed, but that doesn't make any sense, right? So there's no other logical thing you can do, right? You're just stuck with one. So if you have one generator, you're a cyclic group. Now, the key, of course, about cyclic group, real fun facts, is if you have one generator, then a to the n times a to the m equals a to the n plus m, right? So you've got that nice exponential rule. It's, of course, commutative, so all of them are abelian groups, right? They're all abelian. So that's the same. So it would seem like, wow, all cyclic groups are the same. There's actually a lot of differences, though. One other point about cyclic groups is that the reason we use the Z10 is, just as a reminder, is Z10 is literally the set 0, 1, 2. Z10 is literally this set. The integers up through 9, including 0, and the group operation is addition modulo 10, right? And that is a realization of this group, right? So, for example, for Z10 here on the chart, you see a to the 10 equals 1. Z10, because of the Z, that literally means these numbers, right? So this is probably a little shaky notation, right? Because Z10 is literally this set, and yet it talks about the generators here. I guess the way you would have to do this is you would have to say Z, if you wanted to be super strict, you'd have to say Z10, whoops, is the group generated by the number 1 such that 1 to the n equals 0, right? And you have to understand that 1 to the n actually means 1 plus 1 plus 1 n times, right? And it's all mod 10, right? So I'm a little bit uncomfortable with that, I guess, but I mean, it's a minor point, but it is, Z10 is literally to be understood as this. But this is so typically used to represent, or it's not a representation the way we're using the word representation because these aren't matrices. Although you could say this is 1 by 1 matrices, right? You could say these are 1 by, the matrix 0 and the matrix 1, right? And then your addition is is still mod 10, meh. But it's a realization, and just understand that Z10 is literally drawn from this idea, right? Okay. Now, as a reminder, cyclic groups have subgroups, right? So this is what our explorer is calling Z6, which is the cyclic subgroup of Z6. I'm going to actually write it as isomorphic to Z6. We haven't reminded ourselves on how isomorphisms work, although hopefully you remember. But we're going to call this thing Z6. And it's very clear that Z6 is a group of order 6, right? You apply A once, you get A. You apply it again, A squared all the way through A to the 5th. But it's also true that if you apply A to the 3rd to itself, you get back A to the 6th, which is E, right? So there's definitely a subgroup that is E and A to the 3rd, and it is also cyclic because it has one generator, right? You could write this as A to the 3rd, such that A to the 6th equals I, right? So it is a cyclic group of order 2. And so being a cyclic group of order 2, you would say this is isomorphic to Z2. So you know that this cyclic subgroup has a subgroup of order 3. But it also, I meant order 2. This is a cyclic, this is a group of order 2, right? But it also has a cyclic subgroup itself of order 3 because you could go A squared, A to the 4th, and then back to E, right? So it also has the group E, A squared, A to the 4th, right? Which is disjoint from this one except for the identity element. So it has two subgroups, but you can also, you can kind of see how this works, right? Any divisor of 6, there's going to be a representative cyclic subgroup in there. So in fact, if I pump this thing up to 8, now this is no longer a cyclic subgroup because A3 now generates the whole group, right? So the reason is you would get A3 equals A6, and then A6, A3 equals A1, and then if you keep going, you'll get A1, A3 equals A4, and then A4, A3 equals A7. And so what have we got? We've got, and then I guess E, A3 equals A3. So we've got 3, 1, 4, 7, A7, A3 equals A10, which is A2, right? So 3, 4, 2, they all come up. So you generate the entire group. So A3 is now a generator of the whole group. And the reason, of course, is because A3 is relatively prime to 8. So any number here that's relatively prime to 8 is going to generate the whole group. So those 3 will generate the whole group, but 2, 4, and 6 will not. But now what you notice is that A2, A4, and A6 are all part of the same subgroup generated by A2, but it's also generated by A4 or A6. It's generated by any of these. No, I'm sorry. It's generated by A2 and A6. A4 is another group, right? Another subgroup, A4, which generates, which is a subgroup of order 2. Again, the point being that any of these factors that are that share a common divisor with 8 will generate an actual subgroup. So that's the point of cyclic subgroups, is that they have, that's the point of cyclic groups, is that they have cyclic subgroups that are related to the divisors of 8. I mean the divisors of the order of the group. So if we were to do a subgroup lattice here for Z8, it would look like this. It would just have these groups just sort of lined up right on top of each other like this. But this cyclic subgroup feature is not, this subgroup lattice, despite the fact that these groups look so darn similar, the subgroup lattices are going to be radically different. Like, let's look at Z5, right? Z5, it's a prime number, right? So there's literally no subgroups for Z5. So Z5 is going to have a subgroup lattice that looks trivial. But if we look at Z6, right? Z6, well, it'll have a subgroup. It has a generator of Z2 will generate the whole group. So there's certainly A squared would be in there. And A cubed would be in there. But they're not subsets of each other. But they both go back to E. So that subgroup lattice would look like this. And notice this one is lower in the lattice than this one, because this should be of order 3 and this is of order 2. So the structure of the subgroup lattices for cyclic groups is completely related to the factorization of the order of the group. So the factorization of 6, the factorization of 8, the factorization of 5. If we did this for 10, right, Z10, it looks a lot like Z6's. And of course, why not? Because 10 factors into 5, 2, 1, and 10. 6 factors into 6, 3, 2, and 1. So they both share the idea that its factorization structure, I don't want to say it's sort of similar, but it's got an odd largest factor, and then the second one is 2, and sure enough, it's similar enough that the subgroup diagram is the same. But take a Z9, right? Z9, well, it would have a subgroup of A cubed, which has a subgroup of just E, right? So that looks a little different from these. And it's all about the way this number is factored. So that's kind of cool. Now we can use our normal group rule, right? So Z8 has an order of, the order of Z8 is 8. This group has an order of 4, and 8 over 4 equals 2. So we know that this group is normal, right? Now we don't know about this group, whether it's normal. That is, we have to check to see whether, G times this subgroup generated by A4, which I'll symbolize like that, times G inverse equals A4 for all G in Z8, right? Turns out it does. You can check it. And just as an example, I'll calculate it right here, right? And what I'm doing is I'm multiplying on the left by A cubed, which is a G that's in ZG, and I'm multiplying on the right by A fifth, which is the inverse of A cubed, because A cubed times A fifth is A to the 8, which is the identity. And then you bring these two in on E, and you get A to the 8, so that's going to be the identity. And over here, you add it up, and you get A a to the 10 and a to the 10 is a squared, right? So this set at the end is equal to that set. So a to the third certainly checks the box. A to the fifth will check the box too. So now what's left is you got to check a to the fourth and a to the sixth. But if you do, you'll find out that this is normal in Z8, right? It's normal in Z8. Now, why isn't that a surprise? Well, we said earlier, all these cyclic groups are abelian. So all we had to do was remember that. And every subgroup of an abelian group is normal, right? So that was the easy way to do it, right? So this is just sort of a little bit of a reminder. And likewise, this guy, it's abelian. All the subgroups are abelian. So this guy's also normal in, so A4 is also normal in A2, right? And of course, E is normal in these things as well. So that is what cyclic subgroups are. A quick review on cyclic subgroups. Now, if we go back to the Group Explorer stuff, this gives us a bit of a handle on all of these guys that are labeled Z. So it gives us a handle on those, oops, on those, on this one. Now, this one, it doesn't give us a handle on that yet because we haven't studied direct products. But, you know, immediately, a lot of these small groups are just these cyclic, subgroups of that order. And there's a cyclic subgroup, obviously, for every order. And this is a case where, you know, you can see immediately how to generate these cyclic subgroups, right? You just a squared, a cubed, a to the fourth, a to the fifth, a to the sixth. All of these, a to the seventh, you just, the z to the n is just a, where a to the n equals I. So this is a pattern in group theory that does in fact repeat and is very, very easy to stay on top of. Now, the pattern for D4 is a little bit different, right? We've studied D4, and here's our D4 group, right? So now the question is, well, how does this relate to D5? Well, what you see is that D5's group presentation is, the answer is the secret's in the group presentation, right? You look at D5 and you say, well, they both have an involution, right? A squared equals 1, and they both have the same relation, right? This relation here. But the difference is, again, in just one exponent. In other words, the rotation exponent of the dihedral group, if you think about it in terms of these polygons, this rotation idea is changing by 1 every single time. Let's see if that pattern holds. D6, sure enough, you get b to the 6th. D7, everything's the same, b to the 7. And then somewhere, do I have a higher dihedral group? Yeah, I guess D9. Here's D9, b to the 9. I feel like I missed D8. Yeah, D8, b to the 8. So this is pretty clear, right? There is this pattern of groups that we can call d to the n, and evidently d to the n, the only distinction is you're dealing with these, the second generator's exponent is climbing, but otherwise the correlation is the same. However, if we go back, we might ask ourselves, wait a minute, but where's D3? Where's D2? And what's going on is that for these very low order groups, things kind of get crowded out, right? The space gets very crowded. Let me erase this stuff here. But D3, let's look at S3, right? Let's look at S3, right? This almost looks the same, right? You've got an involution, although they call the involution B here, and you've got something that would normally be, if you switched A and B, this would be looking pretty good. You'd get the involution A, and then you'd get B to the third. But switching symbols, we can do that all day long, right? So that's the most trivial thing. So we're just switching symbols. So say we switch symbols on the relation, and then we would get A, B, A, B, A equals B inverse. But the problem is ABA equals B inverse is not BAB equals A inverse. So S3, on its surface doesn't seem to, well, it's on the surface it has a different relation. Well, that's not even on the surface. It doesn't have the same relation. So let's forget this idea of switching these out. Let's use this as presented here. But then take a note that BAB equals A inverse. Multiply both sides on the right by B. And then you get B squared AB equals BA inverse. And the B squared is just a flip. So that is B is the involution here, right? The B is our involution. So B squared is just the identity. So I can erase that. And then I can write ABA equals BA inverse B. Oops, what am I saying? ABA equals BA inverse A, right? I'm multiplying on both sides by A. And so what happens now? Well, the A inverse clearly cancels by definition, and I get ABA equals B. But in this language, B squared is the B is the involution, so this equals B inverse. So now this does look exactly like the dihedral group, just with A and B flipped. So basically, S3 is isomorphic to D3, because now we've seen that the presentation follows the pattern correctly, even though we have to change this presentation the way the Group Explorer did it. So why didn't the Group Explorer call this D3? Well, arguably S3 is more important. And so it decided to call it S3, and it says, well, you're using the Group Explorer. You're smart enough to know that S3 is isomorphic to D3. Likewise, D2 is ultimately, what is D2 iso? So let's do this for D2. What about D2? Well, what's the pattern for D2? Well, the pattern for D2, normally it goes like this. It goes B to the N equals, I think, what are these? The involutions are A, right? A squared equals I, and then it's ABA equals B inverse is the relation. Hold on, I got that backwards. This is it. So this is our typical set of relations for the dihedral group n's, right? So Dn is defined that way. So now I replace n by 2, first of all. So this becomes supposedly D2, and this n becomes a 2. And now what happens over here? Well, it's always been the case that BAB equals A, right? Because A inverse, A being an involution, A inverse is A. And then I multiply on the left by B, and I get B squared AB equals BA. But notice at this very low dimensionality, B is an involution also. So this goes away, and I get AB equals BA. So for D2, I can get rid of all this, and I can just write AB equals BA, only for D equals 2. Well, that one already exists. That's V4, right? That's V4. So this would be something that we might call D2 in this pattern. So the names of these groups, we have to stay on top of them a little bit, but let's look a little bit at D5 now. So we looked at D4. Let's see what are the differences and similarities for D5, right? Let's take a look at that. Certainly the multiplication table is a place you might tend to start. And we see that the multiplication table, still there's only 2 generators in the group. So there's the rotations and flips, if we like to think of this group in terms of the symmetry object, right? Rotations and flips. We don't have to, though. We can think of it more abstractly as just the results of this multiplication table or of the literal presentation. Now we notice that we're going to have more words than we did before because this is a group of order 10. So the new word, I think, is FR squared. So R squared no longer commutes with F, right? That was something that happened in the square, but doesn't happen here. So that's important to take note. And then FRF is a new word too, and it seems like a word is missing, which would be R to the 4th, right? R to the 4th is not the identity anymore. Now the identity is R to the 5th. So where's R to the 4th? So if you look at R squared, you get FRF. And so obviously there's the implication of the table is that R4 equals FRF. And so if we wanted to check that using the generator and relations, how would we do that? And I think it's pretty easy. You just write down the correlation. You multiply on the left by r to the fourth, which is the inverse of r. So that gets rid of it over here, but then r to the fourth on the left appears there. Then you multiply on the right by f, and you clear that, and you get r to the fourth equals FRF. So that explains this. Now, it doesn't explain why you would do it, right? It's not clear to me why on the table they didn't just put r to the fourth, which would be nice because the cyclic subgroup, there is a cyclic subgroup here, a relatively obvious one, r squared, r to the third, and the cyclic subgroup contains r to the fourth. So it seems to me that that's the way you would want to write it down. But the way they would have to write it down is all this and then suddenly FRF at the end. So I'm not sure what their motive is there, but usually these things have a logical reason. It's just not completely obvious to me. But anyway, this is the multiplication table for D5. And in it, you can, you know, first of all, that there's 10 elements in the group. So now I like to right away look at the subgroups. I don't know if that's just an artifact of how I was taught. Subgroups was just such a big, important subject because, you know, cyclic subgroups, which we just discussed, normal subgroups, the center of a group, these are all subgroups. So understanding subgroups was always the way that I understood groups. And I'm sure that's totally legit, but it's where I go first. I think the Cayley diagram is where the group explorer likes to go first. For example, the Cayley diagram, so let's talk about the Cayley diagram. The Cayley diagram, these arrows, the green arrows and the red arrows represent the generators, or actions by the generators, right? So this green arrow is the action represented by multiplication by r. And we have to think of it, I believe, as multiplication on the right by r, because you imagine starting at the element E in the group, right? And then you multiply on the right by r, and you end up at the element r, right? And that's indicated here, and that's an r there. It's a little hard to see, but there's an r, that the group is labeled r. That point represents r in the group. And then if you multiply it again by f, you would get ERF equals the group element RF, and that means you move along this red line. Now, if you have an involution, you don't need arrowheads, right? So R is not an involution, but F is. So with the involution, you don't have any arrowheads. So then if you multiplied by R again, you would now go this way, and you would land at F. So that would be ERFR, and that is the same as F. So RFR equals F. And we know that's true because that's that's one of the defining relations of the group, right? F. Now notice here again, the defining relation has an inverse there, but again, F is an involution, so again, it's one of those weird things. I don't know why they did it that way. Okay, so you've got that, and we could actually look at this unit, this element RFR, where I had to do this very long, complicated calculation, and I am kidding about that. But the alternative is to say, well, is it true? And if you have the Cayley diagram at your disposal, I can just go, okay, R squared, R to the third power, R to the fourth, and I land at FRF. So now I know that R to the fourth is, in fact, FRF. Now, if these things weren't labeled correctly, I could have said, well, FR takes me to FR, and then F again takes me to FRF, and there I am. So I definitely know that the procedure FRF and the procedure R to the fourth are the same. And so the way you're thinking about this is the Cayley diagram is dependent on really the notion of group actions. And I don't think we can discuss the whole idea of group actions now, but it's an important topic we have to get to, because ultimately in Lie groups, remember, every one of our Lie group elements, which was a matrix, acted on a vector space, right, as a transformation to give you another vector in the vector space. So this is an example of a group element that acts on another set to give you another element in that set. So a group action phi takes an element of the group, it takes an element of some other set S, and it returns another element of that set. So the point about group actions is the Cayley diagram is sort of is a canonical group action, because to define a general group action, I need to come up with a set that's going to be acting upon. But if all I have is a group and I don't have another set, then I can't talk about a group action. However, whenever you have a group, you definitely have another set, and that other set is the group itself. So the group acting on itself is it's kind of a trivial group action, but we need to think of it in terms of I take an element of the group, in this case, say any element of the group, R, F, R, and let me take one that we're actually using in our language here, F, R, F. And I can take that and I can take any element of the group and act on it with RFR. And the way that would work is you take the identity element and you go, oops, I said FRF, right? FRF, and you land there. But I could also take this element and I could do FRF, and I land there. And every element is going to go to a different element of the group. No element's going to come back to itself as long as the group is acting on itself. So every element of the group basically drives a permutation of the group elements themselves. And that's an important concept. It's a very, very powerful concept in group theory, and it allows you to prove all kinds of really cool things, especially when you start introducing sets that are not the group. Now, the reason this is called canonical, right? This word canonical shows up a lot in mathematics, and we dealt with this in the What is a Tensor series. But if all I do is create a group, I automatically have the possibility of a group action from the group to itself. So I don't have to add anything new. Once I've created the group, there's no new concepts I need to create in order to get this particular group action. And there's a few other canonical sets that automatically exist when I declare a group. For example, there's when I go to the we're going to create the subgroup lattice, right? This subgroup lattice, once I declare the group, there's a subgroup lattice, and these are all the subgroups of the group. So there is a set of all the subgroups of the group D5, right? It contains the identity group, it contains D5 itself, and then all these other subgroups, which is the group generated by R, that goes there, and then the group generated by a flip, and that goes there, right? And then the group by flip R squared, flip R cubed, flip R, and then flip R to the fourth. Now, these flip R cubed and flip R to the fourth are not part of the language that we've chosen for this multiplication table, but they're still legitimate subsets. The point is I can now have the set of all subsets, flip R, etc. And that set exists automatically when I declare the group. So I could create a group action that takes an element of the group, an element of the set S, and goes to S, where this is the set S. And that would also be canonical, because I'm not really declaring anything new, right? This set pops into existence as soon as I say D5 exists, right? I'm studying D5. If you're studying D5, you're also studying this, no matter what. You can't get away from it. Ergo, any action between G and S defined this way is considered canonical, meaning you don't need to add any new ideas or introduce any new sets or mathematical constructions to define this thing. And there's a few others. We won't get into all of them now. But anyway, we have filled out our subgroup diagram, right? This is D5 up here. And we talked a little bit about the Cayley diagram. This is a very important diagram. And there's also, the Group Explorer is really big on these cycle graphs. And so these cycle graphs, it's good to talk about them because we talked about cyclic groups, right? Well, what are the cyclic groups among the subgroups of D5? Well, R is certainly a cyclic group, right? R is the cyclic group defined by R to the fifth equals I, right? So it looks like that. And that shows up in this cycle graph. You start at E, and it's very much like the Cayley diagram, except it's organized only by cycles, a cyclic subgroup. So you see you multiply by R, you multiply by R squared, you multiply by R cubed, and then you get to R to the fourth, which they're calling FRF, and then you get back to E. So here is a little picture that tells you, whoa, you've got a cyclic subgroup of order 5. And you can see because it's a little loop that begins and ends at the identity. And likewise, all of these guys are cyclic subgroups of order 2 that begin and end at the identity. And this is where you start seeing things that make D5 very similar to D4 and D3. You'll always have a cyclic subgroup of rotations that is of order n, and you will always have all of the involutions. And how many involutions will you have? You'll have n involutions. One is the generator involution, and then there's one for each rotation that's possible after that. So it would be FR, FR squared, FR cubed, and FR to the fourth. I forget which one of those, which is which. Oh, wait a minute. This is FR to the fourth, and I think that's FR cubed. So D4's cyclic graph should look the same as this, right? So let's look at D4's cyclic graph. So here's all the same things for D4, and if you look at its cycle graph, well, here you go. Sure enough, it's got 4 involutions, and there's its cyclic group based on just the rotations. Now, one thing that's important to note is that there's another cyclic subgroup in here that's missing. It's this one, right? R squared is a cyclic subgroup. So what they do is they don't, in these cycle graphs, they typically do not show all possible cyclic subgroups of the larger. They take the largest cyclic subgroup, put it on the cycle graph, and they say you're smart enough to know that all of the factors of this group, all of the divisors of this group will yield yet another cyclic graph. And in this case, you only have one additional one. But if you looked at it for D6, you would end up with something that looks like E. It would look like this, and then you would have an additional cyclic group that would look like that. And you should know that. And yet another one that looks like that, right? But those are never drawn on the cycle graph. They only do the big one, and they assume you know the rest. But regardless, all dihedral groups are going to have this kind of structure. It's going to have, and sometimes, by the way, again, if it's an involution, they'll just connect it with a single line, right? Just keep that in mind. All right, so let's pop back into the subgroup lattice for D5, right? Now, remember what the subgroup lattice for D4 looked like, and without even filling in the actual subgroups, right? I mean, you don't even need, without the subgroup names, you know a few things. You know, first of all, that this group up here, this is definitely D5, and that's definitely E, right? You know that right away. And over here is the subgroup lattice for D4. So you know immediately this is D4 and this is E. So the idea, though, is that you know that there are 3 subgroups that have higher. These 3 subgroups all have the same order because they're at the same level, right? These 5 subgroups all have the same order because they're at the same level in the lattice. That's usually how this thing works. And subgroup inclusion, of course, is by the lines. What's important to note here is that even though the dihedral group's cyclic structure is very, very predictable, right? Meaning we know that D4 looks, we know as soon as you see D4, you know that the cycle structure looks like this, right? With 1, 2, 3, 4 of these guys, right? You know right away. And with D5, you know it's the same thing with one extra dot up here and one extra line up here. And if we wanted to figure D6, we'd put one there and another one down here. And that's for all the D's, this is the system that is used. This is the progression for all the different dihedral groups, which is given as either dn or d2n, depending on your source. So that's very predictable. But the subgroup lattice structure is totally different. The subgroup lattice structure is completely dependent, well, it's largely dependent on the order of D4, right? So the order of D4, which is 2 to the third power, right? It's 8. And the order of D5, the order of D5 is 10, right? Which is 5 times 2. And Lagrange's theorem tells us that, okay, all the subgroups have to have order either 5 or 2. So you know right away that this guy has order 5, right? This guy here is order 5, and these guys have order 2. But what's interesting is you also know that it's impossible for 5 to have any subgroups because 5 is prime. And Lagrange's theorem says the order of any subgroup of the subgroup must, the subgroup is still a group, so Lagrange's theorem applies just as well there. So you would expect that there's no possibility of a subgroup that lies between 5 and the identity. Likewise, no subgroups can exist between 2 and the identity, right? But all of these subgroups of order 2, they can be subgroups of the larger group, but they are not subgroups of any other intermediate subgroups. But with 2 to the third power, now you have all kinds of factors are possible, right? You have 2, you have 4, and, well, I guess 8 and 1. So I guess that's not all kinds of factors, but it's more than... the point is, it's actually the same number of factors, isn't it? Right? So we have 10, 5, 2, and 1. So they both have 4 factors. The difference being is that this factor here, 4, right, is in fact divisible by the other factor 2, which allows for these kinds of relationships, right? These relationships where these subgroups are subgroups of these groups. Now, just because these are divisors, these subgroups have an order that divides the order of a different subgroup, doesn't necessarily mean they must be subgroups. As far as I know, there's no rule like that. But in this case, in the case of D4, that is exactly what happens. The point is that the lattice structure of the group is dependent on the factorization of numbers, which is a very deep number theory issue, right? Is, the factorization of numbers and prime decomposition is one of the big mysteries of mathematics, I think you could arguably say. So even in the sequence of groups that is designed in a highly predictable way, namely the symmetries of, polygons, right, squares and I guess pentagons in this case, you see that the group lattice structure, the subgroup lattice structure, follows a pattern that is completely independent of the sort of the geometry, as far as we know, right? It has to do with these prime numbers. Here's D6, by the way, right? And 6 just again 6, 3, 2, and 1. So it has 4. It has 4 factors. Wait a minute, that's not right. Of course. See, I'm falling into my own trap here, I'm getting confused by the things I'm warning you not to be confused by, right? The order of D6 is 12, right? The factors of 12 are 12, 6, 4, 3, 2, and 1. So presumably, what would we have? We would have groups of order 6, groups of order 4, groups of order 3, and groups of order 2, right? So again, this group of order 3, it has this subgroup of order 3 has no subgroups. These subgroups of order 6, they can only have subgroups of order 2 or 3. And indeed, they have the one group that is of order 3 is a subgroup of all of the subgroups of order 6. And then various groups of order 2 are subgroups of these guys. What's interesting is you don't see here any case where there's a group of order 2 that's a direct subgroup of the larger group. I don't. Maybe we'll come across an example of that later. mean, in other words, finding a subgroup of relatively low order that's directly a subgroup of the larger group without any intermediaries. It'll be neat. We'll find an example of that. And then groups of order 4 are here, so it's all cool. Now these guys, so now, all right, so let's push some of these buttons, right? Let me first fill out these names. So here are the subgroups for order 5. So let's take a look at this. Which ones are the cyclic subgroups? So if I push the cyclic subgroup button, which ones show up? Well, the ones that show up are all the ones that have a single generator. So everything here is cyclic, right? Except the group itself. It's kind of fun to see. So the group itself is not cyclic, but all of its subgroups are cyclic, right? And of course the identity is always cyclic. So what about normal subgroups? Now, I previously uploaded this lesson with just this ridiculously absurd misinterpretation of calculating the normal subgroups for this group. So how do we approach the normal subgroups? And there's two ways, of course. You can do the calculation for each group, and never hurts to repeat these definitions. But what we're looking for is a group, some subgroup H, such that H is equal to all of its conjugates, right? So for every G in the group, this has got to be true. And you can test that for each one of these. Now, we're given one for free because the other thing we remember is that the index of the subgroup R in G equals 2. And we did learn that if the index of a subgroup in the overall group equals 2, then that group will necessarily be normal. So in this case, the order of the subgroup generated by R, that equals 5, right? That's 5 right there. And then the order of the whole group equals 10. The order of D5 equals 10. And of course, 10 over 5 is 2. So 5 will definitely be normal because its index is 2. So how about these other ones? Now, in the previous version of this, I made the absurd mistake of saying that, well, abelian groups are cyclic. And that's true, right? Abelian groups are, in fact, cyclic. But just being abelian does not make you normal in D5. I don't know how I possibly could have confused that. But it is true, all of these groups are abelian. This group here is abelian. All the cyclic groups are abelian, but they're not necessarily normal, right? So what we'll look at is we're going to just decide, are these guys normal or not? So let's just do a calculation for, say, F. So what we'll do is we'll take EF, which is this subgroup right here, and let's just test it with something real simple like R. So we're basically looking for R here and R inverse on the R on the left, R inverse on the right. Is EF going to equal, will this return EF for us? So what would we get? We get the set R to the fourth, and then R to the fourth, right? That's what comes out of this. Well, R to the fourth is R to the fifth, which is E. So this becomes E. And then R to the fourth, well, we know R to the fourth from the multiplication table. We know R to the fourth equals FRF. So I can write this as RF FRF. And then, of course, this cancels, and so we end up with R squared F. And so the final resulting set is E R squared F, which is not equal to EF, right? So right away, we know that this is not normal. You can repeat this exercise for all of the others, and you'll discover that they are all not normal. So the only normal subgroup is this one. And if you'd watched a version of this before and for some reason you've come back because you noticed it was re-uploaded, this is why. I don't know how I screwed that up last time. Okay, let's make one other quick comment about this. Let's see first. So if you push the normal button, you get that one button. What's the center of this group? Well, what are the elements that commute with everything in the group? What elements of D5 commute with everything in D5? In D4, there was some elements that commuted with everything. It was this guy right here. That guy was in the center. And being in the center, that was cool. So it had a center that wasn't trivial. In this case, the center, which if we push the center button, you'll just get the identity element. The identity element is the only thing that commutes with everything. So while I'm correcting some stuff or covering some stuff, there was something I said previously which also wasn't exactly right. It was about okay, so these subgroups here, let's look at these guys here. They're not normal. So the question is, well, what is their normalizer? What is the normalizer of these groups? So I'm interested in this. I'm interested in the normalizer in the group D5 of the subgroup generated by F. So now we know that the normalizer of a subgroup is itself a subgroup. And there's actually a couple definitions floating around that, for example, there's one definition out there there's one definition of the normalizer that doesn't demand that this be a subgroup in here, right? This, you could say the normalizer of any set, any subset S, where S is a subset of D5, not S is a subgroup of D5, right? So this would be the notation for S as a subgroup, and this is just some arbitrary subset. So you can always have a normalizer of a subset and a normalizer of a subgroup, right? So the functional definition is kind of the same, but the principles are a little bit different in the sense that the way it's used is you can very frequently, under some definitions, if you see the notion of the normalizer of something, whatever that something is, you assume it's a subgroup, right? But in some definitions, it's a subset. But we're interested in the normalizer of a subgroup. And what's important is that the normalizer of a subgroup is itself a subgroup of D5, right? And the subgroup itself is always a subgroup of its normalizer, right? Now, the subgroup, so the definition of the normalizer sometimes plays around with what subgroup that is a normalizer of F are we talking about? And the answer is we're looking for the largest subgroup that is intermediate between F and D that normalizes F, right? The largest one is the normalizer. I think in the last lecture I might have said the smallest one. I don't know why I would have said that, but it's the largest one. And it's a subgroup, right? So then the other thing that's true is that in this construction, the subgroup F will be normal in its normalizer, right? In its normalizer. So this is always true when, of course, we're dealing with the definition of normalizer that applies to subgroups. So that is always the case. But it is not necessarily true that the normalizer need not be normal in D5, right? It's only true that the subgroup is normal in its own normalizer, but the normalizer does not need to be normal in D5. Now, in this circumstance, what's interesting is that there's no subgroups between these non-normal groups. Remember, this guy here is a normal subgroup, but none of the others are. So, well, I guess to be technical, of course, the identity is always normal, and what's in key is that every group is normal to itself. So D5 is normal in itself, right? Trivially, but there is no subgroup between that could possibly be this normalizer for F that's intermediate between F and D5. Now, I've seen definitions that insist, well, if that's the case, F has no normalizer, right? I've seen other definitions that say, no, then F is its own normalizer, and it's called self-normalizing. So, regardless, I just wanted to point out that this is supposed to be the largest intermediate subgroup between F and D5 by some definitions. Other definitions allow the normalizer to be the group itself in circumstances exactly like this. But notice, if you did decide that F was its own normalizer in this circumstance, which is fine, I mean, it is true, no matter what you do, it's always going to be true that G, H, G inverse equals H when G is an element of H, right? Not now, to be truly normal in the whole group, it would have to be for all G in G, but this is for all G in H. I mean, this is always going to be true for that restricted number, right? And the normalizer would be for all the G's for which this is true when you go through every G in the group itself, including G's outside of H. But if you accept this self-normalizing definition, this is a good example then of if you consider F to be its own normalizer, then clearly you have a normalizer that is not normal in the overall group. And that was another point I wanted to make, is that the normalizer of a subgroup is not necessarily normal in the overall group. Okay. Anyway, so there is that interesting thing about definition. The definition of normalizer applying both to just an arbitrary subset, which is legit, but when we do it, we almost always apply it to a subgroup. Okay, so enough about that. All right, so in this video, we looked at the group D5, and we compared it a bit with D4. We did that comparison through the subgroup lattice, where the differences are striking, and then we noted that the cycle graph, and likewise the Cayley diagram for D5 and D4 are strikingly similar. I don't think we, let me see, here's the cycle diagram for D4, and you'll notice the cycle diagram for D5 is the same with just with 5 points on the outside and the inside. So the cycle graph and the Cayley diagrams for these dihedral groups are exactly the same, but it's very important to see that the subgroup lattices are very different. And then we talked a little bit about the structure of the subgroup lattices and the order of the group. You know, there are rules, by the way. I made it seem like there was no rules whatsoever about what groups are subgroups of other groups. There are things called the Sylow theorems. The Sylow theorems that we'll talk about later that are very important, that help us decide what subgroups must exist for groups of various orders. And they're very, very important, and we'll have to learn them. So we'll review those very soon as well. But in our next lesson, we're going to go through this group, A4, and we're going to start talking about permutations as representations instead of generators, which is what they do here in the Group Explorer. And we'll look at its subgroup diagram just like before, and we'll look at its Cayley diagrams, which we have here 2 different versions. Okay.
So I'll see you next time.